Hello, hello. This is Nico, and in this Science with Nico, we are going to take a look into the combustion of ethanol and how to calculate the molar heat of combustion of a hydrocarbon, such as an alcohol. Now, ethanol as a fuel can really burn quite nicely, which makes it very desirable. It's potentially renewable if you produce it from a green waste cellulose source, or the husks from corn, for example, via fermentation. And it's safe to handle and transport as a liquid, just like petroleum. And on top of that, it can be used in internal combustion engines without a complete redesign of the engine. And so that makes it really quite desirable as a fuel and really puts it on the map as a potential replacement for fossil fuels. Alright, let's take a little bit more look into combustion. Okay, so if we have a little close look at the combustion of ethanol, what we can see is that ethanol reacts with oxygen to form carbon dioxide and water. Specifically, for every 1 mole of ethanol, it reacts with 3 moles of oxygen to form 2 moles of carbon dioxide and 3 moles of water when it reacts as a complete combustion reaction. And when doing so, it produces quite a lot of energy. Specifically, it's an exothermic reaction, which means it's given out heat. Alright, and it produces 1,367 kilojoules of energy per mole of ethanol, which is pretty cool. That's about a fifth of the amount of energy that octane produces, which is quite significant in comparison to other liquid hydrocarbons. And so, just note here, if we have a look at this a bit visually using the structural diagrams just down here, we can see that for every 1 mole of ethanol, we require 3 moles of oxygen to react and form 2 moles of carbon dioxide and 3 moles of oxygen. Alright, before we get into what the molar heat of combustion is, let's take a look at a quick little challenge, just to see if everyone's paying attention. Alrighty, so ethanol is often called a clean burning fuel, alright, and it burns cleaner in air than octane. And right now, it's your challenge to explain why. Now, just remember, with these challenges, the idea is for you to hit pause on the video and give the question a go at home. So, the question is, ethanol burns cleaner in air than octane. Explain why. And as a hint here, start with the equations for ethanol and octane. Alright, so just remember, hit pause, give the question a go yourself, and once you've done that, hit resume, and I'll go through an answer to the question. Okay. Now, here we go. Let's have a look at those combustion equations, just when we look at explaining this challenge. Alright, so here we have the complete combustion of ethanol, where 1 ethanol molecule reacts with 3 oxygen molecules to form 2 carbon dioxide and 3 water molecules. Here we have octane, where for every 2 octane molecules it reacts with 25 oxygen molecules to form 16 carbon dioxide molecules and 18 water molecules when it reacts to complete combustion. Alright, already just from looking at that, what we can see is that for every 1 molecule of ethanol to undergo complete combustion, which is the most ideal combustion because we don't have any nasty byproducts of combustion, of incomplete combustion, like carbon monoxide, which is really, really bad, it's quite poisonous, and we don't have soot, which can cause all sorts of nasty problems for ourselves in terms of breathing it in and the environment. Alright, we require 3 moles of oxygen for that to actually burn. Now, in comparison, if we consider ethanol, for every 2 moles, we require 25 moles of oxygen, which is a lot. Alright, that's massive. Alright, specifically, that means we need 12.5 molecules for every 1 octane molecule for that to undergo complete combustion. And on top of that, if we actually look at the amount of carbon dioxide produced on complete combustion, ethanol produces 2 moles of carbon dioxide, which is, it's not good, but it's not much, and it's very little in comparison to octane, which produces a whopping 16 moles of carbon dioxide for every 2 octane molecules, or if we look at that just to 1 octane molecule, that's 8 molecules to every 1 octane molecule that it undergoes combustion. Alright, and so what that means is it's producing 4 times the amount of carbon dioxide in comparison to ethanol. Alrighty, now this above problem just here, this is actually compounded even further when we look at the products of incomplete combustion of both of these fuels, with ethanol producing far greater quantities of carbon monoxide and soot particles than what ethanol can produce. Combine that with the reduced CO2 emissions, and what we have is we have ethanol being really quite the cleaner fuel than octane. If we add that to the point that we can actually produce ethanol from renewable sources, then we can actually potentially have a fuel that, while not perfect for the environment, we're at least not stuck with it being a limited supply fuel. Alright, and that's why we're actually far more interested in ethanol than many other alternative fuels to fossil fuels, because it's really quite viable to actually use as an alternative. Alrighty, let's get on with this. Onwards and upwards. Okay, let's look at the molar heat of combustion. Now, the molar heat of combustion is the amount of energy that's released, or the heat that's released when 1 mole of a substance, if we take a look at ethanol here, for every 1 mole of ethanol that reacts with 3 moles of oxygen to form 2 moles of carbon dioxide and 3 moles of water, is the amount of actual energy that's released under this circumstance. Now, if we were to look at this from a theoretical perspective, what we can actually do is we can look at the heats of formation of each of these chemical species. Specifically, if we take a look at this, ethanol has a heat of formation for the bonds within that molecule to actually form. So the carbon-hydrogen bonds, the carbon-carbon bond in the middle here, the carbon-oxygen bond, and the oxygen-hydrogen bond to form from the elements, just the pure elements reacting together, requires 277 kilojoules per mole of ethanol. Now, likewise, carbon dioxide requires 393.51 for the double bonds between carbon and oxygen to form, for it to actually form from the pure elements, and water, for each of the 2 oxygen-hydrogen bonds within that, requires 285.83 kilojoules per mole. Now, one thing that you might be a little bit surprised is that because oxygen is actually the pure form of the element, and it's the most common form of the element, under this theoretical perspective of looking at how elements form and how bonds form, that technically has a heat of formation of 0. Alright, and these values, you'd find these values in a reference book. You'd look them up. Okay, and we're just using this as an explanation to look at where that energy value, how much energy is actually released when a mole of ethanol is actually combusted completely. So if we take a look at this, alright, and so we look at our combustion as being the total amount of energy in these 2 chemical species just here, our 1 mole of ethanol to our 3 moles of oxygen, alright, and we subtract from that the total amount of energy in our products, our 2 moles of carbon dioxide and our 3 moles of water. What we can do is we can actually find out the molar heat of combustion. That's the amount of energy released when combustion occurs for ethanol, and that's simply by taking the total bond energy of the reactants and subtracting the total bond energy of the products. And so we have a look at this, we do some quick maths, just tallying up these values here. We end up with the reactants having a bond energy of 277 kilojoules, and we'll subtract that from the rather large amount of bond energy in the products, which is 1644.51, and we'll end up with 1367.51 kilojoules per mole. That looks familiar. That's the same number as what we quoted for the molar heat of combustion. And that's how we can get to that number theoretically. But we're not going to do that in class. All right, that's kind of a bit on the nose, and it's a bit tedious and a long way to actually, and a hard way to calculate molar heat of combustion. There's got to be an easier way to do that. And as it happens, in the school classroom, we can do that in a really straightforward way by doing a very simple experiment. All right, so if we take a look at that, and we'll just move these out of the way, and we take a look at finding the molar heat of combustion by experiment, what we can do is we can do this using a very simple experiment. Whereas if we have a calorimeter, all right, essentially just a metal container containing some water, and we suspend that above a spirit burner containing alcohol, what we can do is we can track the release of energy from that burning alcohol and work out how much energy is released by tracking the temperature of the water and how much it rises by as the alcohol combusts. And as you know from the preliminary course, if we have a temperature change in a known quantity of water, we can work out the energy. All right, and we can then compare that to the total amount of alcohol that burned, and that lets us find a very good estimate of the molar heat of combustion. All right, so let's take a look at the exact process, the steps we would have to do to actually find our molar heat of combustion by this experiment. Well, number one, we have to look at the enthalpy change. That's delta H. Okay, that's the amount of energy required to raise the water suspended above our spirit burner. All right, and so we do that by measuring the raise in the temperature of the water. We have to know the quantity of water. All right, so we need to know the mass of the water. And once we have that, we calculate the delta H, that's the enthalpy change, using delta H equals minus m cat. All right, where m is mass, c is the heat constant for water in this case, and delta T is the change in temperature in kelvins. All right, once we have that quantity, we then have to look at the spirit burner here where we're combusting our alcohol. And from here, we take a look at the moles of fuel burnt using first just a simple mass balance where we find the mass of the combusted alcohol, first by taking the initial mass and subtracting the final mass from it. Then we find the moles of the combusted ethanol, in this case here, all right, by taking our mass of ethanol and dividing it by the molar mass of the ethanol, right, to find the moles of ethanol. And so once we have our value of energy that was captured by the water, all right, and we have the total molar quantity of alcohol that was burnt, we can then move on to step 3, where we take delta H from step 1 and we divide it by the moles of fuel burnt to find the heat of combustion, or specifically the molar heat of combustion. And that lets us, in a very simple experiment, determine this rather fundamental constant for the energy released by a fuel. Alrighty, so let's take a look at a worked example of that by doing another challenge. Okay, so here, this is going to be a bit of a lengthy one. Alright, now just remember with these challenges, the idea is you hit pause, give it a go yourself at home. Alright, so this lets you actually come back to these videos and review what we're doing, because there's some questions there for you to actually review that make you think about the content in the video. Alright, so in this challenge, students, much like yourself, have carried out an experiment to determine the heat of combustion of ethanol using the pictured setup just here. Alright, and what you need to do is you need to calculate the molar heat of combustion of ethanol using the data that they collected in this experiment. So if we have a look at this, they have a tin can, alright, in which they have a thermometer, and they have 200 grams of water. Alright, they have that sitting on top of a gauze and a tripod over a spirit burner containing ethanol. And during their experiment, they kept track of the water temperature and the mass of the spirit burner. And what they saw was that the water during their experiment rose from 20 degrees to 75 degrees as they combusted their ethanol. And the burner mass dropped from 37.25 grams to 35.50 grams. Alrighty. Just remember, this is a challenge, so hit pause, give it a go yourself when you're reviewing this topic. And when you're ready and you've given it a go yourself, hit play and I'll go through the answer with you. Alright, don't forget, hit pause, give it a go yourself. Okay, let's look at answering this challenge. Alright, first things first, with any problem-based calculation, you need to identify the data in the question. Alright, now conveniently for me, I've already done that just here, okay? And so let's just have a little look at how I found the data in this question. Okay, so first and foremost, we need to know the mass of the water that is found in the tin can held above the spirit burner. Alright, you can find that from the diagram just here. So I've got that written as M for mass. I like to put the chemical species in brackets after my letter term for when I'm describing a variable in an equation. I find that to be a clear way of doing a calculation, and that's 200 grams. Alright, our delta T, our change in temperature, we can find that from the student data. So 75 minus 20, so our final minus initial. Alright, so 75 minus 20 gives us a change of temperature of 55 degrees, from which we will need to calculate an enthalpy, a delta H value. And we also have a mass of ethanol combusted. Alright, we can work that out from our initial minus our final mass of the spirit burner, which comes out at 1.75 grams. Okay, there is also two other pieces of key information that you are expected to be able to not only remember, but expected to know where to look for them. Alright, and you'll find these on the data sheet in the HSC exam. Okay, and you'll also find them and be able to work them out from the periodic table. Alright, now we have the heat capacity of water, alright, which is 4.18 joules per Kelvin per gram, and you can find that in one form on the data sheet. And we also have the molar mass of ethanol, which is 46.1 grams per mole. Now, you're going to work a lot with ethanol, so it's just going to be one of those molar masses that you will remember. Okay, now let's just move this out of the way as we worry about answering this question. Alright, the first thing we have to do is find out the amount of energy that was captured by that water as it rose 55 degrees. So our first step is to find delta H. And we do that using this familiar equation from the preliminary course right here. Delta H equals mcat, where m is mass, c is the heat capacity of water, 4.18 joules per Kelvin per gram, and delta T is the change in temperature. In this problem, 55 degrees. Alright, and what we do here is we just plug our values in. We have 200 grams of water, heat capacity of water doesn't change, and we also have our temperature change. And that'll give us 45,980 joules out of the equation. As long as we have grams, we leave the constant, it's 4.18 when we're working in grams, and we have our change in temperature, alright, which can be in either Celsius or Kelvin, because it is change, it's the same. It's the same actual change. And then it's useful to convert that to kilojoules given the scale we're working at. Alright, so that gives us minus 45.98 kilojoules. Okay, now once we've found that, our next step is to find the number of moles of ethanol that has combusted. Alright, and to do that we need to use the molar mass of ethanol, and we're going to actually use this other old familiar equation from the preliminary course. Moles equals mass over formula weight, or molar mass. Alright, and that'll be 1.75, that's our mass change of our spirit burner, that's the combusted ethanol, divided by the molar mass of ethanol, which will give us a molar quantity of 0.0380 moles. And then finally, to find the molar heat of combustion, what we will have to do just here is we will need to take our delta H from step 1 and our molar quantity from step 2 and divide delta H by the moles of ethanol that were burnt. Okay, just like so, just here, to give us a value for the molar heat of combustion in kilojoules per mole, which gives us a value that is very, very close to the 1367 kilojoules that we know 1 mole of ethanol actually combusts. Now, given that this is a student experiment, we know there's going to be some problems. Okay, they're not going to necessarily have done a particularly accurate experiment. But that is also a consequence of the method that we just described and that these students used. Okay, there are some things that you need to actually take into account and some expectations of not finding the exact value. Alright, let's take a look at those expectations. Okay, so when we talk about using the described method for finding the molar heat of combustion, this is the method we're going to be using in the school laboratory. Alright, there are 3 key assumptions that you need to be aware of, and you should read these. These are key assumptions that are being made for us to be able to calculate our very good estimate of the molar heat of combustion, but bear in mind they do introduce problems that mean that we're not going to have the most accurate molar heat of combustion. We still will find a valid result, but it won't be the most accurate molar heat of combustion. Alright, now the first assumption that you need to be aware of is that generally, unless noted otherwise, no heat is assumed to be lost to the environment. Now that's just not true. Alright, your flame from your spirit burner is emitting heat in all directions. Okay, so there's just no way that all the heat is going directly up into that aluminium can at all. Alright, the second assumption is that the calorimeter, i.e. the aluminium can, is a perfect conductor. Alright, and all the energy that hits it from the spirit burner, from the combusting alcohol, is transferred directly through it, and none of it's lost or reflected away from the metal surface. Now, again, also not true. Alright, the calorimeter will have its own absorption of energy. Alright, and you would need to potentially take that into account if you wanted to find a more accurate value. Alright, and finally, our mass of water, which is typically going to be around 200 grams if we use a aluminium drink can. Alright, we assume that has an even distribution of heat throughout that mass of water, and that's not going to be true. As you heat that water up, you will get convection. Water will rise. It'll rise to the top, and then as it cools down, it'll have a convection current back round, like so. Alright, and so none of these assumptions that you actually need to make to do this calculation are 100% true, but you can still make a fairly accurate estimate of the heat of combustion, the molar heat of combustion. But generally you often will find a value that is approximately half of the theoretical value if you were to use equipment that you would find in a professional laboratory that investigates the molar heat of combustion of fuels and other chemicals and looks at exo and endothermic reactions. Now, generally, chemists will try to use a piece of equipment called a bomb calorimeter. All right, and by bomb I don't mean explosive bomb. By bomb I mean a well-insulated metal container that is, we understand the thermal properties of it very, very well, and it's really well calibrated, so we're able to keep track of energy that is released by a chemical reaction or sucked in by a chemical reaction that takes place inside it. Now, a bomb calorimeter has the kind of following general layout. We have our central bomb, which holds our sample. All right, and that'll be ignited using typically, in the case of a liquid hydrocarbon fuel, using an electrical source, possibly from a battery. All right, there'll be a supply of oxygen that's fed in, so you have complete combustion of your chemical species in there. All right, and the bomb, the metal container that's the bomb, will be very carefully calibrated, so we know how much heat is stored by it and whether or not any heat doesn't pass through it into an outer jacket, typically of water, sometimes oil. All right, that'll be held in an insulated container. All right, with a stirrer to move the water or oil around. All right, so it's uniformly heated by the energy released, or in the case of an endothermic reaction, sucked in by that chemical reaction that takes place inside the bomb. All right, and we'll have a thermometer that will be again calibrated to the device that will actually tell us the exact temperature change of the water or oil jacket surrounding the bomb. And we'll use that to find a very accurate value in a professional context. All right, now this type of equipment, you need to know it exists, but it is not available in a school. And one of the things they like to ask in the HSC examination and trial HSC examinations are possible practical improvements you could make to this experiment in a school. And if you say use a bomb calorimeter, you're going to get 0. So let's challenge you right now. What are some practical improvements that we could actually make to the method we've been describing to actually get a more accurate molar heat of combustion? So just remember, hit pause, have a little think about it, have a go yourself. All right, the idea of this is to use it as a review tool if you return to this video and just to confirm what you know about the topic. All right. Okay, so don't forget, hit pause, and then we'll go through. Then you can hit play once you've given it a go, and we'll go through the answer. All right. So there's kind of 2 key improvements that you can make, all right, with a simple setup in a school. All right, one is to move the flame closer to the aluminium can. All right, this potentially stops energy from spreading out from the flame. All right, as much. You're always going to lose some of the heat to the environment, and you should be expecting to lose approximately half on average. All right, but you can minimize that loss and keep it just at a 50% loss by having the flame as close as possible to the aluminium can. And another alternative would be to use some sort of insulating heat shield that reflects energy lost to the surroundings back to the experimental setup, and you could surround your experimental setup using that. Okay, and that's another alternative. All right, you'd have to potentially construct that from an insulating material like polystyrene, and maybe even line it with some aluminium foil on the inside so it reflects heat back towards the experimental setup. Okay, let's look at wrapping this up. So, in review, let's look at what we've covered in today's Science with Nico. Alright, so we have looked at the combustion of ethanol. Alright, we've looked at what the molar heat of combustion means and how to calculate it from experimental data. And we've looked at measuring the molar heat of combustion experimentally. Alright, mainly in the context of in the school laboratory, but we've also had a little bit of a comment on how you could actually do that in a professional laboratory using a bomb calorimeter. Alright, thank you for watching. If you have any questions, feel free to comment below or to ask in class. Alright, until next time. Bye.